air resistance and terminal velocity. We have talked about air resistance in the previous chapter. We can also call air resistance a drag. Air resistance is like friction. It tries to oppose movement of objects through the air. Air resistance force depends on the speed and the shape of a moving object. And we have to mention that cars are designed to have a low drag coefficient. A drag coefficient is a measure of how easily an object moves through the air. In this figure, we have different shapes of objects moving, and the lines represent air path. We notice that an object's movement is easier when it has a streamline shape, and the drag coefficient, CD, is very low. That's why they designed cars as a streamlined shape, so that the air doesn't affect its movement. So as we see here, a streamlined shape and the drag coefficient is very low. Now if we have shapes like those, these will have a harder movement because they have more corners and they will be affected more by the air resistance. So streamlined and smooth surfaces produce less drag and have a low drag coefficient. Now the drag force increases with the speed of the object, and it affects the way dropped objects accelerate. The faster they get, the greater the force opposing their motion becomes. Like the free fall case, we have two forces, the weight of the object and the drag opposing it. In page 30, figure 3.13, we have here three cases. The first one is at the point of release of the ball. The velocity is 0, therefore the drag or the drag force Fd is equal to 0, and we only have the weight mg acting on the ball. The resulting downward acting force is just the weight force. This force makes the object accelerate towards the earth. Now the second case shows the object now moving. Because it is moving, it has a drag force. The drag force acts upwards against the movement. This means that the resulting downward force on the object is mg minus Fd, since here the mg is bigger than the Fd. Also, the acceleration is smaller, and the object is accelerating. It is getting faster. The faster the object moves, the bigger the acceleration. Now, the third part is when the drag force has increased to the point where it exactly balances the weight force. So here Ft equals mg, and since there is now no unbalanced force on the object, its acceleration is also 0. We can say that the object here has reached its terminal velocity, and although it is still falling, it will not get any faster. We can see these three cases in the graph of figure 3.14 that shows a velocity time graph on the free falling case. The graph at first is an increasing straight line, then it reaches a point where it stops increasing. Here it reached maximum acceleration. And if we want to get the terminal velocity, it is the intersection with the y-axis. The dotted blue line shows how the graph would look with negligible air resistance.